bases, their strength, and we're also going to be looking at a type of reaction called neutralization reaction, which is a type that fits into our 5 standard types. And so I was saying that out of the millions and billions of reactions that happen, a lot of them just fit neatly into one of the 5 types we've studied. Acid-base neutralization reactions is an example of one that fits neatly into our predicted types. So that's what I'm going to discuss today. So Unit 5, we're still in chemical reactions. Lesson 4, acid-base strength neutralization reaction. There will be 6 or 7 lessons in this unit. So we're actually, like I said, we are going to be more than halfway through after today. But next week we take a pause, we do a lab, then we do review and quiz, and then we'll finish up the rest of the chapter the week after. All right, so Unit 5, Lesson 4, make sure you write it down. We're going to be learning today about acid and base strength. We're going to take a quick review of the pH scale and what that means. We won't be doing any calculations today because I was holding off on math. Unit 6 will be where we do the math of the course, Unit 6 and 7. So mentally prepare yourself for that, but we'll just be talking about theory today. So Unit 5, Lesson 4. Today we're going to go over acid and base strength, specifically acid strength and neutralization reactions, along with a brief review of pH. Giving you a little bit of time to write down the title of the lesson before we get started. Just to give you a heads up, I'm moving forward in about 20 seconds. If you missed this slide, you can look on the board here at the title of the lesson. It's really just acids and bases. Welcome back. All right, the lesson title's up there. I'll leave it up a little bit longer for you. We're about to get started. First thing we're going to go over is something called acid-base theory, and we're only going to learn right now something called the Arrhenius theory, which is the most basic theory of acids and bases. The Arrhenius theory tells you the following, so you should write all of this down. An acid is a compound that, when placed in water, dissociates and makes H+. What does the word dissociate mean? What do you think? Separate. So, just in case you don't know that, let's write that on the side. The thing about science classes, there's a lot of vocab, like tons of vocab, and understanding the language is half the battle. Dissociate means to separate or break apart. Yes. And where you've heard of it before, like associate versus dissociate. Associate means like put things together, dissociate means take apart. So compound that when it dissociates in water, it yields H+. What does yields mean? We did learn that. So like creates, and that was where we put that chemical reaction arrow, right? That means that as a product, you're going to get H+. So I'm going to write out a couple of simple equations that illustrate this via example. And so for acid, you would have something like this. HCl, when placed in water, breaks up to become what? What are the ions it would actually break up to become? I place HCl in water. What are the ions? When it dissociates, it would become H+ and Cl-. So dissociation means breaks apart to form ions, the individual ions that are in this compound. And let's take a look at another simple one. Simple meaning it's as easy as I could possibly give you. NaOH, and this is a very common base. The definition for base is it's any compound that when it OH minus will be produced. So in its most basic form, how would NaOH break apart in water? It would break apart to Na. What's the charge of Na? Plus 1. And it would be OH with a negative 1. And so any compound, when it breaks apart in water, if it gives me H plus ions, I know that that compound is going to be an acid. Any compound, when it breaks apart in water and it gives me OH minus ions, that's going to be a base. Another way to understand this is if I have HCl, I put it in a beaker, and this is how it's going to be presented to you next class period on Tuesday. You're going to have a beaker, and it's going to say HCl in the front. This means that in that water, you have H plus ions in that water, and you have Cl minus ions in that water. And the water surrounds the H plus, and the water surrounds the Cl minus. We learned about that back in Unit 4, if you'll recall. The water surrounds the positive ion, and the water surrounds the negative ion. And if I have a beaker filled with NaOH, this means that I have Na plus ions in that beaker, right? And I've got OH minus ions in that beaker and a bunch of water around the Na plus ions and the OH minus ions. And so that's just another way to visually understand what's going on. Because once again, what's going to be presented to you, not tomorrow, but next class, which for us is tomorrow chemistry, next chemistry class, is you're going to be given beakers with these different solutions in them. And they're going to form reactions. And so it's important to understand the vocab, but then what does it mean in simple equation form? And what are you actually going to see? And what does that mean? So this is called the Arrhenius theory. There are further acid-base theories, but for now, we're going to keep it simple. We'll look at other parts of acids and bases later on. I'm introducing this one layer at a time. So for now, acids are H plus, acid, OH minus is base, and that's what we're looking for. And so how can we link that to what we've learned before in a middle school science or even a late elementary school science course? What we learned about in elementary school was something, or middle school was something called the pH scale. So we're going to review that real quick and what that actually means. I'm giving you a little bit more time if you need it. You should have the definitions for acid and base, and you should show that in equation form. So, what does this dissociation, what does that actually mean? What does the separation look like when you see dissociate? Bleach is a base, actually. Never mix bleach and ammonia. Never do it. What happens? Death. It makes a gas that if you breathe too much of it in, you go to the hospital, you die. The Cl2. The Cl2 gets released, yeah. And we don't want to mix it. And that's why they tell you never play with your household chemicals. Never play with your kitchen cleaners. Right. Because it's a base, but it is very dangerous. For Cambridge exams, like for AICE chemistry, I don't see them use bleach very often, and I think the reason why is because ammonia is always something that we need to use on a Cambridge exam, and they don't want students to, they always tell you don't mix things you're not supposed to mix, but they don't want students to make an accident and mix those two. On the Cambridge exam, you will have to predict what happens from this mixture, for example, and you see a color change or a gas. You'll see next lab when I teach you a couple of things, how you could go and be like, oh, I know that's hydrogen gas that it's made. That's the type of prediction you would have to make on a Cambridge exam. Like, how do we know it's hydrogen gas that's made? You saw something explode. That is actually how the lab exam is. It's actually pretty cool if you think about it. But there's a reason they don't give bleach very often on that exam. I think it's for safety reasons. They don't want to give students something that could possibly cause harm. Very cool. Very cool. So, next class, that's what I said, I'm excited for next class when you guys have that lab because you'll get kind of a preview of what qualitative analysis is. So, yes, the pH scale, you should write this down in your notes. It goes from 0 to 14, and really, you should know that it goes from 0 to 14, where neutral pH. Anything between 0 and 7 is acid, right? An acid solution. And anything between 7 and 14 is a base solution. But what does that actually mean about the solution, about the chemicals that are in the solution? That's what I'm interested in covering as a chemist with you. If we have a neutral solution, this actually means that we have the same amount of acid and the same amount of base in the solution. So you should write down the amount of H plus equals the amount of OH minus. In a neutral solution that has a pH of 7, it's not that you don't have acid. It's not that you don't have base. You actually have both, but you have both in equal amounts, so they neutralize each other. There's a very famous compound where the H plus is equal to the OH minus. And so what compound do we say is always neutral if it's pure? H plus and OH minus. We've been going over what is that? What is H plus and OH minus? If I have both in a compound. That compound is? Water has a neutral pH because it has equal amounts of acid and base, not because it has neither. So be careful with that. And so in an acidic solution, you would have more of which one? H plus or OH minus? What would you have more of in an acidic solution? You always have both, but which would you have more of in an acidic solution? Based on the definition you saw here. If the pH is less than 7, you would have more H plus, right? And if you have a basic solution, this means you have more of OH minus. And there's one more thing. I told you I'm really not going to get much into the math today, but I am going to state one thing. Every movement of 1 on the pH scale is actually a movement of 10 times more acidic or more basic. So you may want to write that down. Every movement of 1, every difference of 1 on the pH scale indicates 10 times more or less acidic. Which means that if I have a solution that has a pH of 4 versus a solution that has a pH of 7, how many more times acidic would a pH of 4 be than a pH of 7? If every movement of 1 is 10 times more acidic, it would be 10, 10, and 10. So if I measure that I have a solution that has a pH of 4, it is actually 1,000 times, because 10 times 10 times 10, 1,000 times more acidic than a solution that has a pH of 7. The math behind that we'll look at later in the year, but just in theory, it's something that's important to understand, because when people say, oh, you know, you're drinking something that has a pH of 2, well, now you know a pH of 2, if you're drinking something that has a pH of 2, maybe something that has some phosphoric acid in it, like soda, is somewhere between 2 and 3. We're talking that it's 10,000 to 100,000 more times acidic than just drinking pure water. And then think about what that does to your teeth. And that's why your dentist tells you, don't drink soda. Also the sugar. Bacteria feeds on sugar, so every day. And later on in the year, I'm going to do a specific pH lab when we learn how to do the calculations, and you'll be able to put a pH meter in each solution, including soda and other things, to see what the pH is. It's a cool lab that I do later on in the year. But for now, we're in theory. Right now, it's theory and ideas. So make sure you have the pH scale down. What you need to know at this point is that if you see a pH of 7, this means you have the same amount of H plus as OH minus. If the pH is less than 7, you have more H plus. pH is more than 7, you have more OH minus. And every movement of 1 is actually 10 times more or less acidic or basic, depending on which way you're moving, of course. All right, that was just review. Review pH scale. And know what you need to do. So then the first type of question, practice question, write this down, is write the dissociation for each of these acids or bases. How do they break apart and why? And so you've got HBr, you've got H2SO4, and you've got BaOH2. So think about what I showed a couple of slides ago. How would you write the dissociation for each of the following acids or bases? How would they break apart? What are you going to be allowed to use if you're unsure about the polyatomic ions charge? What did I give you as a resource last class that I said you could use for a quiz or a test? Solubility rules, right? So there's a couple polyatomic ions in here, just throwing that out there. First one doesn't have a polyatomic ion, so how does HBr break apart in water? So if we're talking about dissociation, we're saying, how does this break apart in water? If I was to place this in water, it would turn into, what is the first ion you would have? H is always positive, right? So H would be +1, and then for the state you write AQ because it's still dissolved in water. And so anything AQ is dissolved in water, in its ion form, and water surrounds it. And then what is the other charge? Br would have a, right, because it has to balance and the ends become 0. And this would be the answer for the dissociation. What does this mean? You've got HBr in water, you've got a bunch of H+ ions in that water. So this would be, what do you think? If we had a solution of HBr, do you think the pH would be higher or lower than 7? What's your prediction? You have a solution of HBr. Would you have a pH higher or lower than 7? If you've got H+, you don't have as much OH- as you have H+, then it's going to be a pH lower than, maybe your prediction, 7 is greater than the pH, or pH lower than 7, you could say. pH should be lower than 7 if you've got a solution of HBr. H2SO4, let's try that one. What's my first ion here? It is always H with what charge? +1. Remember, it has to be +1 because hydrogen has 1 electron. Only 1 electron can be taken away. So it has to be H +1. And what's our other ion? Sulfates. Can you find sulfate's charge? Either on your chart or you remember it, it's -2, right? So I've done the dissociation, but I'm currently not done. What have I still got to do? Do I have the same amount of each atom on each side right now when I broke it apart? Or is something not balanced? Something's not balanced. I have 2 hydrogens here, don't I? So this should have a 2 in front. So when you do a dissociation, if you've got more than 1 of something, you've got to put it in the front because it breaks apart. The way to understand it is that in this solution, you've got 2 H pluses and 1 SO for every 1 SO4 - 2. pH higher or lower than 7? Definitely. pH is lower than 7. This is an acidic solution. This is a scary acid, actually, sulfuric acid. I will be wearing gloves when working with sulfuric acid. It is one of the very dangerous ones. It's also dangerous. Because it's still a bunch of H+. And so remember, more H+, means the pH is less than 7. So if you see a bunch of H+ in your solution, without doing the math calculations yet, just you see this is the compound you have dissolved in water, that's going to have a pH lower than 7. The acid in soda is phosphoric acid, by the way. That also will have a pH less than 7. What about barium hydroxide? Barium hydroxide. How would this break apart? What's the first ion here? So it would be Ba with its +2 charge. It has to have a +2 charge. And then hydroxide, you would write your polyatomic ion, hydroxide, and how would I account for the fact that there's 2 of them? How should I write that correctly? Let's put that in the Because it's saying this releases 2 OHs and 1 barium. That's what that's saying when I put it in water. So to understand it graphically, it will look like this. For every 1 Ba plus 2, I have 2 OH minuses in this water. Yes? So what's your prediction about pH? If I just had barium hydroxide placed in water, does it have more or less? It's a base, right? This is a base, whereas these two are acids, because remember H plus is acid and OH minus is base. So if I have OH minus, my pH is definitely going to be greater than 7. Now, what I wanted to show you, and I'm going to repeat this next thing for next class. I'm going to show you now, but I'm going to repeat it next class for those students who are missing, because I'm going to show this in the lab as well, is how could I tell, just given a solution of acid or base, that I have a solution of acid or base? So while you were working on your bell work, I created a couple of solutions. This first one is sodium hydroxide. So I have some sodium hydroxide here. So if you don't mind, I'm going to use this pen. So I've got NaOH. That's sodium hydroxide. I know what I put in here. Like, I know that I put sodium hydroxide in here. But there's a couple of ways we can tell that we have a base. The first one's called litmus paper. Have you ever heard of litmus paper? Some people will have called it pH paper. Right. So we're going to write this down. So litmus paper. If I have a base, the way I can prove, one of the ways I can prove I have a base is I get a piece of red litmus paper. Litmus is an example of an indicator. An indicator will tell me the pH of my solution without doing much work. It is a chemical compound that actually changes color based on how much H plus it has on it. So litmus paper is red in acid and it's blue in base. And so you're going to want to write that. Red means acid and blue means base. This is one of the, that would be neutral. They would, especially after the next thing that I do. So I have this red paper, which starts off, this is the acidic form of litmus. If I put it into my NaOH, like I made this NaOH, I took NaOH, I dropped it in water, and I was stirring it. What is the prediction? If I put this red paper in the NaOH, what color should it turn? The litmus paper. Let's see. So it turns to blue, right? So in NaOH, litmus paper turns blue. And this is because like I said, you'll be doing this with your different solutions next class. But the litmus paper turns blue because what you have is a base. And base will always be blue. I always remember it like that, BB, blue base. So it's a different charge. Now, let's say that I had an acid, and I prepped an acid too. I'm doing some work with the AS class in 6th period today, and I already had some available. This is some hydrochloric acid. So I had prepared some hydrochloric acid last night, actually. And so I have some HCl. And what would we predict if I have the blue form of litmus paper, and I put it into hydrochloric acid that I have prepared? What color should that turn? It should turn red. Let's see. Does that happen? And so, or pink, right? It looks pinkish or reddish, but definitely it did turn from blue to red. And so this means that it's, so litmus turns red when I have an acidic solution. So this is a way to know, okay, OH minus blue, H plus in that solution, more H plus in that solution, it's going to be red. Now there's a bunch of other indicators. I'm going to give you another one next class. That's pretty cool. I remember when I was, actually one of my early memories, when I was probably in elementary or middle school, a magician of sorts was showing this reaction, but they were pretending like it was magic. And I was like, I thought I was magic when I was a kid, and then when I learned chemistry, I was like, they fooled me. This is something that's not magic. So this is actually an acid-base indicator, like litmus paper, but it's a different chemical. It's called phenolphthalein. And you'll be also using this probably next class. But it turns different colors in acid versus base. And so for phenolphthalein, which is a very big name, phenolphthalein, that it's a large organic compound. That's why it has such a complicated name. In acid, it's actually colorless. And in base, it's bright pink, like this magenta pink. And so let's take a look. I'm just going to drop this into the, so I'll take my NOH so I don't mess up my stock. And I'm going to put some NaOH in here. And I will take a look at what color does this change. I just put a couple of drops in with the, like a magenta, right? That's what phenolphthalein does. And so the question is, my phenolphthalein, did you see that? That's crazy. And then it got lighter. Let's see what happens as I add acid. Interesting. Means I don't have enough acid. So what happens as I add more acid? Let's say I have a stock. Color disappears. And yeah, and the magician told me that was magic. Lies. What actually happened? Why, as I added the acid, I needed a lot because I didn't measure. Without the math, it's just like, hey, where did we get there? We'll get to the math, but now it's theory. Why? Eventually, I added acid. That color changed back to colorless. Why? So go ahead. So as I kept adding HCl and like force that H plus in, I eventually get to the point where I got more acid than base. And now the solution turns back colorless because it's a balance. If I've got more OH minus, it's pink. But if I've got more H plus, it turns colorless. So you know both base and acid is in the solution. But once I tip the balance to more acid, now it changes color. Does that make sense, how indicators work? So you'll be playing with this next class in the lab. I just want to show you some things. I'll be showing you some things next class as well before we do the lab. But yeah, I don't know if you saw that reaction before. I saw it when I was in middle school. I had no idea what it was. Told me it was magic and it lied to me. It's not magic. Yeah, if you see science, it's definitely, if you watch science videos, it's definitely one of those classic things to observe in chemistry where you see that color change. So what actually happened when you tip the balance is you're actually reacting the acid with the base. And when you tip the balance, you neutralize the solution. And so the type of reaction I wanted to discuss with you today was called a neutralization reaction. That's what we're going to look at. And the good news is it's really nothing new to learn, and we've already learned it. I just didn't tell you what it was. But beforehand, remember last class there was one type of reaction you didn't get the time to cover. It was on your slides that I had printed for you, but I said we'll just do this later. This is the time. We're going to do this later. So there is in double replacement reactions, I'm going to take off the clothes now. In double replacement reactions, there is specifically, there's two different compounds that you can make that decompose into gases. There's one that I know that Cambridge tests. So I would write this one down. So double replacement reactions, because I know that Cambridge tests this, so this can show up on a quiz or a test. If you do a double replacement reaction, and what you make out of that double replacement reaction is H2CO3. This actually fits neatly into this lesson because that is an acid, isn't it? It decomposes. It actually undergoes a decomposition itself. So when you form H2CO3, it undergoes a decomposition into water and carbon. This is a carbonic acid, and it is actually extremely important because this is the acid that's in the ocean, and which maintains the pH balance of the ocean, and it is the acid in your blood that maintains your blood buffer pH within a certain range. So this reaction, that's why I said Cambridge definitely test this one. It's very important. If you make H2CO3 in a double replacement reaction, it will decompose into two predicted products. And guess what those products once again are? They're water and carbon dioxide. We are actually going to be able to prove this next class because we will have reactions that make this carbon dioxide. If you put a lit flame to carbon dioxide, it will turn the flame off. It will basically deprive the flame of oxygen when you produce carbon dioxide, and the fire goes out. And that is one proof that you have made carbon dioxide gas. And so this decomposition, make sure you write down. So one for the H2CO3. We're going to take a look at a couple questions where this happens with double replacement, and then we'll take a look at neutralization reactions, and we'll be done then. Go ahead. Pass the field. So make sure you're writing this down. It's also printed in your notes from last class. Some students were working ahead on it. The one that I'm asking for you to memorize is H2CO3. H2SO3 does do the same thing, but the one I'm asking for you to know is the H2CO3 one. All right, so these are the complete and balanced questions we didn't do last class that had to do with this. For all the types of reactions, you are responsible to complete and balance. Last class, we learned something called double replacement reactions. So today's lesson is really just also within that realm of double replacement reactions. How do I know this is a double replacement reaction? What tells me here that this is double replacement? What am I looking at on my reaction side to know double replacement is my major type? Go ahead. There's four things. A positive, a negative, and another positive, and another negative. So we've got that A plus, B minus, C plus, D minus situation going on, right? So now, let's identify those ions, because that's the type of reaction we have. What is A plus here? We want to complete and balance this. What is A plus? The first positive ion is barium. So it's barium with a +2 charge. What is our first anion? It's a polyatomic, so you've got a paper that helps you with that, and I did put the back up in the front of the classroom. It is carbonate. So B minus is CO3 -2. What is C plus? H plus. It's acid. That means that you see HCl now in next class's lab, you're like, oh boy, that's hydrochloric acid. Gloves on. And Cl would be our last one. What's the charge of that? -1. So remember, when we do double replacement, we identify our ions. Once we have correctly identified our ions, we make our swaps. We know that A has to go with D, and B has to go with C in the proper order. So let's do this one first. A with B. What do we get out of that for our first product? You're putting BA together with Cl. So you should get BaCl2. So on your product side, you should be writing BaCl2 because your charges, you have to cross them, right? You get BaCl2. What about BC or CB? It should be, right? The other product. What is this? When I put H and CO3 -2 together, what do those make? Because remember, it's A with D and C with B. What do these two make together? We've got H plus 1 with CO3 -2. What does that make? You crisscross, you get H2CO3. Now here's where you have to memorize something. If you see H2CO3, this actually isn't the final answer. What did I say here? If you see you make H2CO3, instead of writing H2CO3, you're going to write water and carbon dioxide, because that actually automatically splits apart. When you do the reaction, you'll see a gas. You'll be like, why does that make a gas? Because this actually decomposes on being made, and it decomposes into water and CO2. Water and CO2. So now what do? We're completing and balancing. What do we got to do next? Is this equation balanced? We've made the formulas. Is it balanced? I've got 2 hydrogens and 2 chlorines on my product side. I've only got 1 hydrogen and 1 chlorine on my reaction side. So what number do I need to put in front of here to make this balanced? And that's actually all you have to do to balance that, just the 2 in front. So is it balanced now? What's the last part of the completing and balancing process we've been going through? It's the formulas, then balance, then what's last? Base. If this is a double replacement reaction, how do I predict the state of BaCl2, which is an ionic compound? We look at the solubility rules. So you have that paper, take out your paper, solubility rules. What do they state about barium chloride? You should be looking at the rule for chlorine. What is the rule for chlorine? It's the third one down, Cl minus. What does it say? It says soluble except Ag plus and Pb2 plus. Is barium one of those? Is it Ag plus or Pb? No. So it's not an exception, so it's soluble. And what does soluble mean? The state of matter is AQ. So you write AQ here. That's the prediction you have to make, that you have to use the solubility rules to make. What is the state of matter for water? Liquid. What is the state of matter for CO2? Gas, right? We're done with that. Okay with this? All of the following questions are all going to be double replacements, which we learned last class, just like specific situations. Let's try this one more time. What are the ions for the second one? I want to bring this one up because this is actually something I'll be giving you in the lab, and I don't want you to get confused there, so I want to show you an example of it first. What are our ions here? What is our A plus? What is our positive ion? It's Na, right? Na plus. So A plus is Na plus. What does that mean B minus is? What is B minus? It's the rest of it, right? So it's this HCO3 thing with what charge? That include all those elements. HCO3 is the other part. What would the charge of that have to be to counter the +1 of sodium? It would be minus or just negative, right? What is C plus here? What is C plus? H plus 1. And what is C minus? SO4, because the thing together is a polyatomic you've got to recognize. And it's SO4 with a -2. Now that I've identified my ions, I can put together my products. Remember that the outer 2 parts go together and the inner 2 parts go together. So A goes with B and C goes with B. So what is AZ? SO4 -2. And that product is actually Na2S4. Okay, Na2. What is our other product? This is where in the lab in the past we got confused, which is why I want to make sure you bring it up. What is the other product here? It's H plus 1 with HCO3 minus 1. How would we put that together? Like, what would that turn into? Think about how that would look. H plus 1 with HCO3, welcome back, minus 1. Would you write HHCO3? Does that sound right? represent itself as actually H. Isn't that H2CO3? Like 2 hydrogens, 2 H's. Does that make sense? That H plus 1 and HCO3 minus does combine to make this. Well, guess what? That's that thing that now you've got to remember. When that's made, it actually automatically decomposes to become water and carbon dioxide. So this will become, every time you see H2CO3, you've got to translate that to water and carbon dioxide. You're going to get a gas out of this. If you do a reaction with this, a gas is going to come out, and that gas is going to be carbon dioxide. So what is our product here for the second one? It's Na2SO4 plus water plus carbon dioxide. That's the rest of it. In our steps, that's step 1, right? Formulas. We did that. Now what do we got to do? Balance. So step 2, balance. Now you got lazy, right? I didn't write the step that said formulas, balance. Step 1, formulas. Step 2, balance. I need to balance it. I got 2 sodiums here, so what do I put in front of here? 2. I think that's gonna not do it. Let's see. I've got 4 hydrogens now, right? Let's try doing this. I got 2 H's and 2 HCO3s. Try putting a 2 here and a 2 here. I think that's 4 plus 2 equals 4. 10. 6 plus 4. Yeah, that's what do we have to do now? Step 3. Comes next. Sodium is a group 1 metal. What does that tell me about its solubility? One of the things that I said definitely memorize last class. Always soluble. Like, you can look at the chart, it's there. But you see that group 1 metal? It's soluble. The answer for this is going to be AQ 100% every time you got a group 1 metal. And then water, we know, is what state of matter? Just straight up got to know water at room temperature is a liquid, and carbon dioxide at room temperature is a gas. And so this was the type of reaction I didn't cover last class. That was in that lesson. Make sure you have it done. So this just means the thing that I'm adding is that if you produce this specific compound, H2CO3, you do need to know that that actually decomposes and will make water and carbon dioxide. Everything. So we're going to talk just a little bit about strength of acids, just a little bit about strength of acids, like what in the world is a strong acid versus a weak acid. But like I said, with the mathematics, we're going to hold on to mathematics till the next unit of study. So today is just theory. But we will be looking at the math that proves it later in the class, in the course. So how can we determine the strength of a compound that is an acid when placed in water? So if you want to, you can write this question. So we're looking at strength of what makes a strong acid versus a weak acid. So how can we determine the strength of a compound that is an acid when placed in water? And really what my purpose behind asking this question is, you know, if you see an acid in front of you in a lab, a beaker filled with an acid in front of you in a lab, I want you to be able to look at that acid and be like, is that dangerous? Will it burn me? On inspection. Like, that's the purpose. When you get to your next lab, you look at it and be like, okay, gloves and goggles. Cleaning the table a little bit. I'm getting the light bulb. So write the question. So what we define as a strong acid and I just want you to write this part. You don't have to write the part about weak acids, just the part about strong acids, because that's the part that really matters here. A strong acid, if you have one, will break up all of its H pluses into solution. That's what we classify as a strong acid. So every H plus it has in the compound breaks off into the water. And that is a strong acid. Strong acids are highly corrosive. They will burn you depending on concentration. But that's what we classify in compound form as a strong acid. Weak acids don't break up all their H+. So you'll see that there's double arrows here, reversible reaction, meaning as some of the weak acid breaks apart, some of the H+ will go back on to the compound. It won't all be dissolved, dissociated in water. And so write down the definition for strong acid. You don't have to memorize the definition for weak. Yes. So there's good news and bad news. The bad news is that we have determined the strength of acids experimentally, meaning that you will straight up have to memorize what the strong acids are. The good news is that Cambridge only asks you to really memorize strong acids, like 3. There are more than 3 strong acids that exist, and there are some properties you can glean for polyatomic ions. For example, the more oxygens there are in the polyatomic ion, the stronger the acid will be. But overall, strong acids are determined experimentally, that they've dissolved everything. The concentration has dissolved everything it can. And so there's a list that you'll need to know, which means on inspection, if you see any of these labeled on a container, I prepared any of these acids for you, that means you're wearing gloves and you're wearing goggles. I'm giving a little bit more time. This is some writing, so wait. In the list of acids I asked you to know a couple class periods ago when I talked about acids, some of these were on that list, so they're going to show up again. Some of these, oh, oh no, never mind, you're good. Are you good? Or you're ready? So the only 3 that you need to memorize, strong acids that you gotta know, are H2SO4. So these are the strong acids that you gotta know by inspection. Are sulfuric acid, H2SO4, hydrochloric acid, HCl, and nitric acid, HNO3. This following list should be memorized. Meaning you see these in front of you, should be very close to. There are plenty of other acids that exist that are not nearly as dangerous. I'm going to shout out a couple. Citric acid. Citric acid we have all the time. It's in fruit, and we actually need vitamin C in our diet. And so citric acid is an example of a weak acid that, although it has some of the properties of acid, has pH lower than 7, it is not one of the very strong acids that would be super corrosive and would really burn you. Another famous one is salicylic acid, which you may not know what that is, but it's aspirin. Aspirin, if you've ever taken aspirin, you've had salicylic. And it's an acid, but again, it's not a strong acid. It's an organic acid that is helpful for pain. Yes. As soon as the person comes back, you may. I'm going to go from the restroom right now. So just these 3 strong acids you should know by heart. Sulfuric, nitric, and hydrochloric. These are the 3 that Cambridge has. And I was saying here that there are other strong acids that exist. You don't have to write this down. But if you see ferric acids by name, HI, HBr, those are also strong acids, but they're actually not tested in the Cambridge syllabus. So when I teach the pre-ACE class, I teach it in terms of this is what you would possibly be in the future. That doesn't mean that it's everything that exists. H2SO4, HNO3, and HCl. Those are the 3 you gotta know. So the final thing we're gonna look at is something called a neutralization reaction. And a neutralization reaction isn't going to really be anything new under the sun. Meaning that we've actually already done neutralization reactions. I just didn't formally define what it was. Right? Okay. So, neutralization reactions. If I took, and you saw what I had done in practice that you'll be doing next class, I took an acid and a base, and I mixed them together, and you saw the color change dramatically from like a bright pink, hot pink, to colorless. What I was doing was a neutralization reaction. I was mixing an acid with a base. And what ends up happening is if you add the same amount, you will get salt and water. And so you're going to want to write this down. A neutralization reaction is a double replacement reaction, where your first compound is an acid, your second compound is a base, and your products are a salt and water. You'll also want to write on the side, salt equals ionic compound. So I could have said ionic compound of water, but this is how people say it. You'll get some kind of ionic compound, you'll get water. All ionic compounds are actually called salts. So make sure you're writing it down. You should write the type of reaction, what actually happens, and then what is a salt. You're mixing an acid and a base, and you're getting salt and water. And it's really just a double replacement reaction. When you see it in practice, you're going to see that we've actually already done this. Anytime you make water as a product, besides the gas decomposition, anytime you make water as a product, you have got a neutralization reaction most likely. All right, I'm giving you a little bit more time, and then we'll get to the last set of practice examples, which is really what this is. So let's go ahead and I'm going to give you a 20-second heads up. I'm going to move forward. Make sure you have written down that this is an acid and a base mixed with salt and water. Salt's really just an ionic compound. And so what we're going to do, and you don't have to write all of the steps because they're the same steps as always. It's going to be to complete and balance. So let's take a look at a couple of neutralization reactions before we leave, and I'll have the homework. So here we go. Complete and balance the following neutralization reactions. So you can just write complete and balance. You don't have to write all of these steps because these are the same steps that they always are. Complete and balance are really. So this is a neutralization reaction, but it's also an example of a double replacement. Why is this a double replacement? Why would we be following a strategy for double replacement? So neutralization is really just a double replacement. We specifically make water in an ion by neutralizing an ion. Why is this double replacement? Double replacement every time you have what? or because hydrogen's not really a metal, remember? It's positive charge, positive charge, and another negative charge. Two compounds on your reactant side. This is the only type of reaction that has two compounds on your reactant side. That's how we know. Two compounds equal double replacement. None of the other types of reactions we looked at in the unit had two compounds. Every time you have two compounds, double replacement. That's the type we're looking at. So then, once we know it's double replacement, we identify our ions. And so our A plus, our B minus, our C plus, and our B minus. What is our A plus here? H plus 1. What is our B minus here? C. L minus 1. What is our C plus here? A plus 1. And our D minus? Right? So what goes together for our products? This goes together. And what does hydrogen and hydroxide make? Water, right? So we know one of our products is water. And what is our other product? What is the other thing that we make? KCl, which is the combination, welcome back, next to the bathroom, which is the combination of the inner two parts, the C and B. Remember, positive ion first, negative ion second. Those these two together. It's K plus 1, L minus 1 equals KCl. What else do I have to do? It's formulas. That's done. Balance. Is that done? Is this balanced? It's not balanced. Okay. There are two hydrogens. Anything else? Keep it short. It's balanced. And then what's the last part? H2O is a water, which is a liquid, so we write L. KCl. Potassium is a group 1 metal, which means ionic compound. We refer to the solubility rules. If I've got a group 1 metal, what does that always mean? Always AQ. Always AQ. Yes? Does it? Stays. So really, a neutralization reaction where we neutralize an acid with a base is just one example of a double replacement reaction. And this is one of the things I was telling you right at the beginning of the unit. The reactions that you study, if you study further chemistry, they fit neatly into these 5 buckets. And then they just have their different applications. Like we know that the pH will change when I mix these two together because I'll have either more H plus in my solution or more OH minus as a result of having more of one or more of the other. But it is an example of a double replacement reaction. And when I have equal amounts of both, I'm going to make water and salt, or what's called a neutral solution. Kind of make sense? All right, so we are done. I'm not going to do the last one because I think we've done a lot of practice double replacement at this time. I want you to get practice before we go. So we're done with the new content for the first half of the unit. We're done with completing and balancing. So this is homework, but you can get started on it. There are 2 parts. The first 5 questions are like this. It's completing and balancing with the neutralization reactions. Basically more double replacement reactions, to be honest with you. And then the last 2 questions are the gas decomposition ones, which is the one where you make the water and the carbon dioxide. Make sure you practice this, turn it in next class. Next class in the lab, not only will you be doing the experiments, but you'll also be completing and balancing all of the reactions you see in the lab. So you do need to get the practice. Here you go. Yeah, you can work together during the class. You want to get started on it. Here you go. stop recording once I have all these up. So I can go to the bathroom. Remember, if you move chairs to work with someone, just move your chair back at the end of class.